So, after talking about confidence intervals in the previous section for different uh, percentiles of a distribution, we're going to talk about a couple of hypothesis tests that we can do to test whether or not the median is equal to its value. So, the first one we're going to talk about is a sign test. So, this is actually data from problem 8.5-1, except I did change one of the data points so that they were all different. So anyway, so here is our 13 data points in this case here. We're going to test the null hypothesis that the median is 40,000 against the alternative hypothesis that the median is actually less than 40,000. So the way we're going to do this first is we're going to let y be the random variable that represents the number of data points in a sample that are less than the 40,000. So in this case, we can actually see that there are 9 of those. If I've counted correctly, there are 9 of these in this particular sample out of the 13 that are less than the 40,000. Now, if the median is really 40,000, we would expect that, given an individual selection from this distribution of the random variable, the underlying random variable where this data came from, we would expect that the probability of selecting a particular point being less than the median is going to be 1/2. So we've got 13 identical trials. All of them have a probability of success of 1/2. So y here would be binomial on 13 trials and a probability of success of 0.5. So we can define critical regions. So for this one, let's just say we define our critical region as the number of selections being 10 or greater, and we'll reject. So this is the number of selections being less than 40,000 is at least 10. You can check that the probability that this event actually happens is about 0.46. That was why we used 10. It was about 0.05. So this test would have that particular significance level. So that would be our alpha in this case. All right. In this case, though, if this is our rejection region, when we had just said that there were 9 of the values that were less than 40,000, we would not reject the null hypothesis. And you can actually check that if the median is 40,000, the probability that you would get 9 or more observations, so that would be calculating a p-value, the probability that you would have 9 or more observations being being less than 40,000 would be approximately 0.1334. We can use a binomial distribution in Excel to do that, for example. All right, so the reason why we call this a sign test is because essentially, if you do the individual differences of each data point and the median, you basically are just counting how many of them are negative because we wanted to go less than 40,000. So that was why we called this a sign test. We're basically counting negative signs. However, the main issue with this particular test, we don't take into account how far below or how far above a particular value is from the median. So, for example, if you look at the 4 data points, 1, 2, 3, 4, that are above the 40,000, the largest one that's away is this one, that 41,229. That's the farthest away from the median. That's only 1,229 away. Notice that most of the other ones, 7 of them in fact, are farther away than that. Like this one's at 36,480, this one's at 31,031, this one's at 30,906. So there's a few of these are significantly lower than the median, whereas the other ones that are above aren't all that far above. So we're not taking that into account at all. All right, so to start taking that into account, we'll do what's referred to as the Wilcoxon sign test. So the first thing we have to do are calculate the signed ranks. All right, so let me show you what we mean by rank. Let's see if I can click this farther down, and I'll get there to the point. Get down to the bottom here, and then I'll talk back through what I just skipped over. So here's the data that we have in our sample. We can rank them from smallest to biggest by difference in their by difference away from the median. So this 39,485 is the closest to the median. It's only 515 away. The reason why we give it a negative is because it's below the median. So this is what we mean by signed rank. So this 39,245 is the second closest to the median. It's below, so we give it a negative. So we've got those 4 values here that are positive, and we've got 9 values that are negative. So there's 4 values above the median, 9 values below the median. And they're ranked by, again, magnitude for how far away from they are from the median. All right. So I'm going to use, going forward, we're going to use I to represent the rank of a sample point, again, with respect to magnitude. Now, it's possible that when we put the ranks in there, we're going to sign it. So it'll be, again, have a positive or a negative depending on if it's above or below. Again, if we really are talking about that we have the median, then the probability that you get a positive rank versus a negative rank should be a half. When you select a data point at random, there's a 1/2 probability that's above the mean. There's a 1/2 probability that it's, 1/2 probability that's above the median, pardon me, and a 1/2 probability that it's below the median. So we should have a particular rank assigned to being I or negative I should be 1/2 in this case. All right. So anyway, again, that's if the null hypothesis is true. All right. So let's let v sub I represent this particular random variable where it can take on the only values that v sub I can take on are I and negative I. Again, each of those probabilities that those can happen is 1/2. And we're going to let v here be the sum of the v sub i's. So we're going to add up these signed ranks, essentially. All right. So the first thing we notice is that if I do expected value, then the expected value of each of these is just the sum of the expected values. Well, notice that the sum of an individual expected value is just 0, because again, we have probabilities of a half, and they take on opposite values half the time. So the expected value is 0, which means the expected value of v here will also be 0, because we're going to add up a bunch of zeros to get the expected value. All right, so what about the variance of v sub I? Well, this is easy to compute. We do expected value of the x squared, if you will, and the x is the I here. I squared happens a half of the time. Negative I squared happens half of the time. We just get I squared. We don't need to subtract off anything here because, again, the expected value is 0. So this really is just the variance. The variance is the expected value of x squared here in this case, or the expected value of v sub I squared in this case. All right, the other thing that we notice is that for a particular rank, the ranks of the data points are all going to be independent of each other because one data point selection doesn't depend on another data point selection. It's just as likely to be higher as lower than the other one. So the expected in particular variables, the particular variables are all going to be independent of each other. So when we do the variance of v, this should be the sum of the variances of the v sub i's. Sorry, not the sum of the v sub i's. This should be the sum of the variances of the v sub i's. So we're going to add up I squared from 1 to n, and we have a formula for that. It's n times n plus 1 times 2n plus 1 over 6. Right? You probably recognize that from calculus or from discrete. You see this summation several different times in mathematics. So anyway, this gives us the mean and the variance of this v, okay, which is good. So now we know a little bit about its distribution. Unfortunately, writing down the probability mass function for v is not convenient. It's not an easy one to write down. Notice I did PMF rather than PDF because v really is a discrete distribution here. It takes on integer values. We can, however, figure out its moment generating function. Remember, we do expected value for each I. We would do the expected value of v sub I, or the expected value of e to the it. We're using I instead of x here, but e to the it. So 1/2 of the time we would have e to the it. The other half of the time we would have e to the negative it. And then we have independent random variables. When we have independent random variables, we can get the moment generating function by doing the product of those things. Okay, so at least we know a little bit about its distribution because we can write down at least a product form of its moment generating function. Now, good news is that we don't really need to know exactly what the distribution is because we know that the central limit theorem, and actually we need a generalization of the central limit theorem because these v sub i's don't take on the exact same values. Their distributions are essentially identical because of the probabilities, but the values they take on aren't equal. So you need a little bit of a generalization of the central limit theorem to get it to work. But as long as n is big enough, this will be approximately normal on its mean, which is 0, and its variance, which is the n times n plus 1 times 2n plus 1 over 6. This is not a huge surprise that this would be the case. Let's just look at a picture. So the curved graph is a normal distribution with that mean 0 and variance what it's supposed to be. This is a histogram based on the probabilities of the V variable that would be from the 13 data points that we had from the previous example. So this would be the probability that you would have a certain number of a certain value out of the sum of those particular signed ranks. So one of the things that you notice here is that each of these probability rectangles here all have a width of 2. The reason why they have a width of 2 here, and you can't probably really see it because I think it's cut off on the bottom of my recording here. I can see that the recording screen, I think, is off of the x axis here. But each of these have a width of 2 across it. So, for example, this one right here is going from 0 to 2. This first one that's right next to the y-axis the width goes from 0 to 2, and we use the probability that happens at 1 for that height of that rectangle. The reason why we're using a width of 2 here rather than a width of 1 for these individual values is because when you add these things up, if you have an even number of terms in your data set, you're going to always get an even value when you do your sum. And if you have an odd number, you're always going to get an odd sum. And that's just the way the things will pair up as far as the ranks go. So you're always going to get either, if you have an even number of data points, your possible sums for your V's are always going to be even. If you have an odd number of data points, your possible sums are always going to be odd. So in this particular case, what I'm saying is that when we go from 1 to 13, the possible sums, if I remember correctly, go from 1 to 91 over here. But in multiples, they all have 2 apart. So it's going to be 1, 3, 5, 7, and all the way down to the 91. And then the same way with the negatives. Anyway, the whole reason why I put this picture on here, regardless of what the scale is and all that other discussion I made, is you can really see that this probability distribution does look approximately normal. So we'll use the normal distribution to approximate these probabilities that we need, or to find critical values and those kinds of things. We can also use the normal distribution to help us approximate p-values, but we'll have to remember that the widths are 2 rather than 1 to help us with a continuity correction here in a little bit. All right, so back to the example we had. Here are the signed ranks. Let's add up the signed ranks. I know I changed it to a W now, and that's in honor of the fact that we call it the Wilcoxon sign test. So this W is just the sum of your signed ranks. So you get negative 55 when you do that. Using our normal distribution, we're going to reject if this W, we're looking at the median being below 40,000 rather than equal to 40,000. So it will be less than or equal to negative 1.645. The negative comes from the fact that we're looking below. The 1.645 here is coming from the Z sub alpha that is at the alpha confidence of 0.05. And then multiplied by the standard deviation here, which would be the square root of the variance for 13 data points. So 13 times 14 times 27 over 6, which is approximately negative 47.077. So this W is less than this critical value, if you will. Notice we're finding our critical value slightly different. We could have just divided the negative 55 by this standard deviation and done essentially a z-score and found that it was less than the negative 1.645. Either way works. It doesn't matter which way you do it. All right, so unlike the first sign test that we did way back at the beginning of this, we reject H0 in this case because this actually took into account the magnitudes, and the magnitudes are saying, hey, this median's probably not 40,000. All right, let's talk about the p-value here real quick. All right, so I mentioned in that previous slide that each of the widths of our rectangles are 2 rather than 1. So when we do a p-value, we have to use a continuity correction of a full unit rather than a half a unit, because those rectangles are straddling a whole unit on either side. So instead of using a half unit correction like we talked about before, we're going to use a full unit. So when we calculate our p-value, we want to make sure that when we're doing our probability, we want this negative 54 to be, we want this to be negative 54 because we want to make sure that negative 55 is hit when we go less than the negative 54. Okay, so that's why I used negative 54 here for the p-value. I'm using a full unit for continuity correction, and I need to make sure I include the negative 55. And now we do, pardon me, a z-value. This is now a z-score. I subtract the mean, which is 0, and I divide by the standard deviation. So I get, this should be approximately phi of negative 1.887, and I'm going to click this, and it's going to go off the screen, so I won't have to read it. It's approximately 0.0296. So just a hair under 0.03. So our p-value here is about 3%. You could actually figure it out the exact p-value by going back and using that moment generating function that I told you about before. You could actually go through and calculate, using that moment generating function, the exact probabilities for each of the particular values for the Wilcoxon statistic, this W, and then add up what would be negative 55 or below. And it's actually close to that 0.0296. I did it earlier, but I don't remember what it is now off the top of my head. But anyway, we'll talk more about this in class, and in particular, we'll be doing a lot of this on Excel.